Welcome to module 23. In this module, we will be looking at water footprint. So, water footprint is another of those categories of footprint that looks at the resource stress and how we can account for water consumption in different production processes. So, the idea for water footprint comes from the availability of water that is present on the earth for our consumption. In the natural systems, the water cycle is what makes water available in various forms for our consumption. So, you can see in this water cycle that water from the oceans and lakes and rivers evaporates, and also there is transpiration from the land system that goes into the vapor form to the atmosphere, and then through precipitation it comes back for water consumption. Once the water comes back, it is available in different forms for our consumption. Most of the times we are reliant on the accessible water resources for withdrawal from these lakes and freshwater systems, so that we can use it for the production process or direct consumption. So, what is water footprint? The water footprint of an individual or community is generally defined as the total volume of fresh water that is used to produce the goods and services consumed by the individual or community. So, this definition was given by Hoekstra and Chapping in 2008. It can be calculated for single product. So, we can quantify how much is the water being consumed for different kind of products, for example, cotton crop, tea, coffee, energy resources, etc. We can also quantify that value for businesses and organizations. The most of the times the unit is volume of fresh water use per year. We will also see in a bit that there are different categories of water footprint that is defined based on from where the water is being withdrawn or how the water is being made available for consumption. With this definition, let us put forward. One thing I would like to clarify is this water footprint is different from watershed scale water management, stream management and urban management or urban water management. So, in most of the cases, you will hear a lot of times people talking about how to manage the stream or how to manage the water resources that are available. That is more of an ecological view of managing water resources in terms of how can we ensure that the water is continually available at a certain threshold for consumption. In the case of water footprint, it is not really a water management strategy, but rather a metric that will help to make strategies for maintaining the water resources or for strategies for water management. At the core, if you remember in ecological footprint, we talked about the actual land requirement to support the production versus the available biocapacity. In this case, at the core, the concept is of stress. In terms of that, what is the available water capacity or what is the available water resources for consumption, and what is the dependence of different production activities at the life cycle scale for water resources or the use of water. So, at the core there is this idea of balance or the imbalance between the demand and the supply of the resource, where the supply is provided by the freshwater resources that are available for consumption and the demand is given by the water footprint or the requirement of water that is there for the production processes. So, there is this concept of virtual water that is introduced for calculation of water footprint. Virtual water is defined as total amount of water that was consumed directly or indirectly to produce the goods. So, remember when we were talking about the life cycle view, we also talked about the direct and indirect emissions or the direct and indirect resource consumption. Here we are talking about that there is of course a direct water requirement in manufacturing of a good, but if you take a life cycle view where you include all the upstream and downstream processes that are involved in the life cycle of that product, there is of course additional water requirement. That indirect water requirement is also accounted for in the supporting water requirement for the production. Hence, that is called as virtual water because that is being consumed upstream. So, here in a simple way, the way we can understand the virtual water, it is the sum of water used in various steps for the production change. You can see that it is not the actual water content of the consumed goods. So, sometimes people get confused into thinking that virtual water means that there is this much amount of water contained in that product, and that is not correct interpretation. The correct interpretation of virtual water is it is the supporting water for the production and not the embedded water in that product. Any product, if you think about a biomass product, there will be some inherent moisture in that. That water content is different than the virtual water of that biomass, because the virtual water is the life cycle consumption of water to produce that biomass, and that supports the upstream and downstream processes. Virtual water hence can also be called as embodied water. We also looked at this definition of embodied resource and embodied emissions when we did the life cycle calculation for direct and indirect resource consumption. So, again, embodied water, do not misinterpret as the amount of water contained in that product. What it means is that it is the direct and indirect water requirement to support the production of that product, and that is where we have the embodied water calculation. The origin of water footprint came into being when we started realizing, especially from the sustainability perspective, that water is also a limited resource. Even though water is a renewable cycle, because the water cycle continues to recycle water at different rate, it is in finite volume that is available at any time of the year, at any point. In different locations of India and also different locations of the world, there is a high water stress because the supply and demand are completely imbalanced. So, when we realized and when researchers realized this idea of that water even though it is a renewable resource available from ecosystems, it is actually a finite resource available at any time of any point of time for consumption. And therefore, they talked about what we call as importing virtual water. So, since virtual water is the indirect and direct water requirement for supporting production, if we are importing product from some other place, in a sense we are also importing virtual water, because that water was not available in the local region for production. So, there is this inherent dependence of one region on the other in terms of virtual water that may cause water stress in the other region. So, from a sustainability perspective, identifying this water threshold and then the water stress caused by the consumption of different region is a very important concept for strategies to do a better water management in the long run. So, let us look at an example for virtual water content of coffee consumption in Netherlands. So, again we talked about virtual water content. So, for tea and coffee, the way it is defined is that virtual water content of a coffee would be the volume of water required to produce 1 unit of coffee or tea. So, remember, it is not the water that we are talking about, that we are preparing coffee and we have that 1 cup of coffee. That is not the virtual water we are talking about. What we are talking about is the production of the coffee beans and how much water has gone into production of per unit or per ton of that coffee beans throughout its life cycle. So, to quantify that water content or the virtual water of the coffee, we define a term which we call as product fraction. So, remember, in a life cycle you have a step by conversion of the product into a final production. So, at each step you have a different final weight of the product. So, if you are a chemical engineering student, you might remember from a separation process. So, when you are going through a separation process, your weight of the final product is not the same as the weight of the initial product, because there is some separation and some waste generation. Similarly, in the life cycle of production of any product, as we go forward, there is a product fraction that we can define, which is the ratio of the weight of resulting product to the weight of original product. So, the definition is very simple. We are simply saying that what is the weight of the final product per unit of product of the original system. And also, based on what process you are looking at each life cycle stage, your product fraction will change. So, virtual water content in that case keep on increasing. So, we will see how we calculate that virtual water content by looking at the product fraction at each step. So, let us look at this example of coffee production through two different pathways. So, here we have a coffee plant, and that coffee plant finally gives us roasted coffee through two different pathways. One is the wet production method and one is the dry production method. And in each of these production method, the drying process or the separation process may be different. So, let us look at the dry production method. In the dry production method, in both of these methods, the first step is that from the coffee plant, we are getting the cherries that are then converted into different products. So, here your coffee plant requires some amount of water, and then when it harvests, it gives some amount of product. So, the first step, if you look at this virtual water that is written for the cherry, is 3028 meter cube per ton. How was that calculated? Here what we do is that we want to know what is the total volume of water input . So, for the total volume of water input, we know that your crop water requirement for coffee plant is about 1277 millimeter per year. You can convert it into per hectare. So, for that we can basically say the depth of the water is 1277 by 1000 meter, and if we want to convert into per hectare, we can multiply by 10,000. So, we have 1 hectare is equal to 10,000 meter square. So, 1 hectare is the area is 10,000 meter square, and the depth of the water is 1277 by 1000 meter. So, we converted the millimeters into meter, and when you multiply this depth by the area, you will get the volume of water that is being consumed per hectare for the coffee plantation. So, that value will come about to be 12770 meter cube per hectare. Now that you know the total volume input and you know the yield of the product, so we have 4.2210 per hectare. So, the yield of the cherry is given to be 4.2210 per hectare. So, now that you know the yield and the total water consumption, we can calculate the virtual water, and your virtual water is basically the 12770 meter cube 12770 meter cube per hectare divided by the yield. So, 4.22 ton per hectare. So, that will give us the value of 3028 meter cube per ton, which means that for each ton of cherry production, we need about 3028 meter cube of water. Now, from there on, you have two different pathways. One pathway is taking through the drying, and you see there is this production fraction or product fraction, which is the weight of the dried cherry versus divided by the weight of the cherry which was wet. Now, with that production fraction, since you are drying, the virtual water content of the final product will increase. So, you will see that the virtual water content of this dried cherry is higher, which is calculated as the virtual water content of your product. So, or the initial product. Oh, okay. So, we can see that the virtual water content of product and that divided by the product fraction. So, here the dried cherry will have can be calculated as 3028 divided by 0.36, and when you do that calculation you will see the virtual product water content comes to be 8395 meter cube per ton. So, this is the way that you can continue to calculate the virtual water content for each of the final product. So, as you go further in the dried production method, you have hulling which has the product fraction of 0.450, and then you have the hulled beans which has higher water content. Then you have polishing and sorting, and then the green coffee is formed, and finally, the roasting also eliminates some of the weight fraction. So, you have final product fraction is 0.84, and the roasted coffee through this pathway has a water content of 22,458 meter cube per ton. Now, of course, this does not mean that this is the amount of water that is contained. This just means that how much water per ton. So, it started with the water input here, and at each step we did not add any more water. See, so your water addition was the same. So, the same volume of water continues, but as we go in the step, because per ton water requirement increases. So, your virtual water keeps on increasing. In this one where you have wet production method, here you will see that your process water is added. So, in this case when you have to calculate the virtual water for this one, you will actually look at the water content here. So, total water input will be 6899 meter cube per ton plus the processing water that is added. So, 5 meter cube per ton, and then you will divide by the product fraction which is your 0.90, and when you do that calculation you will see that there is 7671 meter cube per ton of virtual water. So, the idea is that the amount of water that has entered the production cycle is the same unless you add additional processing water, and based on we assume that the same water is going through that is supporting the production has not changed, and then we keep on calculating the virtual water content at each step as the virtual water content of the initial product divided by the product fraction, and that gives us the final virtual water content. So, here for the roasted coffee in the wet parchment method or the wet production method, we have 22,530 meter cube per ton, which means that from the water footprint perspective, your dry production method is better in terms of the sustainability if we care about reducing the water stress by the coffee production. So, this is a way that you can calculate the virtual water content for different products following different route of processing. So, let us practice this virtual water content calculation through another pathway. So, let us take this activity for virtual water content for tea. In the previous method, in the previous process, I showed how the two different processes for coffee production is. In this one, we have the tea plantation. So, here you have three different kinds of tea being produced: black tea, oolong tea and green tea, and you have the product fractions in some ones are given and some you have to calculate. So, let us take 30 seconds and let us answer this question: what is the virtual water content for fresh and rolled leaves in this case? Okay, so now we have to calculate the virtual water content for fresh and rolled leaves. You can see that here the fresh leaves is formed by just the harvesting. So, what we need to know is what is the total water. So, what we need to know is what is the total water input to the process and what is the actual harvest. So, first we want to know the total water input. Okay. So, since your harvesting yield is given in tons per hectare, so your tea plant crop water requirement will be 917 millimeters. So, we are going to convert it into the volume per hectare. So, divided, this is the meter in terms of depth. 1 hectare is equal to 10,000 meter square. So, we can multiply by 10,000 meter square, and that gives us the water input as 9,170 meter cube per hectare. So, that is the amount of water that is input for the tea plantation. So, if we know the yield, so yield of fresh leaves is equal to 7.10 ton per hectare, and therefore, the virtual water content for fresh leaf is the total amount of water that is entered, which is 9,170 meter cube per hectare, and then the 7.10 ton per hectare. So, this gives us the virtual water content to be 1291 meter cube per ton. So, this value will be 1291 meter cube per ton. Okay. So, from there on you also have to calculate the virtual water content of rolled leaves. So, for rolled leaves we know that is the final product, and the product fraction between the conversion of fresh leaves to rolled leaves is 0.36. So, that is the weight loss. So, we will have the virtual water content of will be equal to the virtual water content of fresh leaf, which is 1291 divided by the product fraction, which is 0.36, and this will give us about 3587 meter cube per ton. So, you can see that the virtual water content keeps on increasing at every step. That does not mean that we are adding more water to the system. That only means that per ton production we are now the intensity of water production, water utilization, or the intensity of water required for per ton production is increasing. Let us look at further calculation. So, let us see what is the PF for black tea. So, take 30 seconds and we will calculate the product fraction for black tea. So, our second problem is to calculate the product fraction for black tea. So, for that one you have the virtual water of black tea known, and you know the virtual water of rolled leaves. So, here simply we will take the virtual water of rolled leaves divided by the virtual water of black tea, and that will give us the product fraction. So, let us look at the product fraction for black tea is going to be the virtual water of rolled leaves. And divided by the virtual water of black tea. So, for rolled leaves that value will come out to be, if you go back, we have 3587 divided by 4978. So, and that value will come out to be 0.72. So, we can fill this value as 0.72. Similarly, you can do all the calculations and you will get the green tea. The virtual water for green tea will be about 4982 and the virtual water for oolong tea will be about 7174 meter cube per 2. So, now that you know how to calculate the virtual water, you can see your final question is we can use this metric to compare the different pathways and say which product is better from the sustainability perspective for water consumption. So, here if you compare your black tea, oolong tea and green tea, your black tea has the lowest amount of virtual component, which is virtual water content, which is 4978 as compared to green tea, which is 4982, and oolong tea is highest. So, in that case, from the sustainability perspective, your black tea is the preferred option if you are cared or if you care about the water stress or the water sustainability. So, following this approach, you can calculate the virtual water content of any product, given that you have the information about the process of each step and how the product fraction is changing at each step, and if you need any additional water for the processing that you need to add additionally. Okay. So, let us go back to the concept of virtual water. So, what this graph is showing or this picture is showing is that how the water is being imported across the world, and you can see that South America and Central America are sending lot of virtual water to Europe, and what it means is that they are not really exporting lot of water. What they are really exporting is lot of biomass based product, and that biomass based product requires a lot of water, which means that Europe is under water deficit because there is lot of water that they need for their own consumption, but now they are actually importing that product, and therefore, you will have more water stress if we had the consumption of the production in the Europe itself. Similarly, you can see that India is actually also exporting lot of product that is requiring water. So, in a sense India is exporting product, but we are also exporting virtual water. So, if we care about the water stress and better utilization of water resources, we really need to understand, are we exporting high virtual water content products, and if yes, is that really sustainable, and is that really the strategy for making the products, or we can improve the virtual water content of those products. So, in terms of calculation of water footprint, what we do is that the same way as the life cycle assessment, when you have the life cycle inventory, we can multiply all the goods and services in terms of weight with the virtual water content. The virtual water content can be calculated using the life cycle approach, and that will be per unit product or per unit ton or per ton. So, whatever unit you select, you will have that virtual water content in terms of, let us say, meter cube per ton, and if you know the total amount of inputs of that particular product to your life cycle, you just multiply and you will get the virtual water content or for that particular product. There is other idea in terms of the water cycle. So, remember that we started with this idea of water cycle that is being affected due to the water consumption. So, there are three types of water components that are seen for the water footprint. One is the green water. So, when the rain falls on the ground, it is intercepted by all the ecological systems, and some of the water goes to the soil and that goes into the plants. That is about 65% of water in hydrological cycle, and that is what we call as the green water, which is the source for rain fed agriculture. So, lot of the rain fed agriculture is also consuming water. So, it is also relying on the water cycle and causing the interruption or the interception to the water cycle, and that is what we call as the green water. The next is the blue water. So, blue water is the part of the water that actually seeps into the ground and it fills the groundwater table and also the river and the freshwater lake, all the runoffs. So, this is the water that we actually withdraw from the freshwater ecosystem and actually consume. So, if you think about our actual water withdrawal for production and consumption, it is mostly the blue water footprint that we consume. So, it is very easy when we are calculating the virtual water content, mostly we are talking about how we are also withdrawing different water, which is the blue water. Last, we also quantify what we call as grey water. So, grey water is nothing, it is the amount of water that is required to dilute the pollutant in aquatic systems to an acceptable limit. So, grey water is we think of grey water as the part of water that becomes unusable because we have polluted the water. With this approach, the water footprint, the actual water footprint calculation, total water footprint calculation goes beyond the virtual water content only. What it does is that now you are going to look at if there is any part of the life cycle that is dependent on the green water, what is the blue water input, which is the amount that we are putting into actual production, and then the grey water, which is if we are creating any emissions and that emissions is going into the fresh water or any other aquatic ecosystems, how much water, what is the concentration limit of the pollutants, and how much water or volume of water you need to put into the system to dilute it to a level that it can be usable or consumable. So, now you can split the virtual water content or the water footprint calculation in terms of green water, blue water and grey water. So, we already talked about the water cycle. The green water is the part that is intercepted by the vegetation and it becomes available as the biomass as rain fed agriculture, and the blue water is anything that is filtrated, percolated and is available into the groundwater or the sea and the lake for our water consumption. So, flow of water components, if you look at the precipitation, if we have 100%, most of the water that we have available on the earth system for our consumption is available through precipitation. It goes into land and soil, about 65% of it gets intercepted and is available as the green water, and from that whatever we get into the biomass or the rain fed agriculture is what we get as the green water footprint. Rest 35% is going into the blue water, and that also goes into either irrigated agriculture, but it can also go for the domestic and industrial water use, and that can form a component of grey water because this water after being used can be polluted, and that is the volume that we need to add that additional volume to dilute. So, you can think of each of the components of your water consumption in your life cycle, and you would then quantify each of them separately to quantify the total water footprint. Most of the time we go by the virtual water content that is available, and that is the straightforward way of calculation of water footprint for any products. In terms of the water sustainability, there is a global idea, there is a global stress that is happening. This data is taken from Rockstrom's paper, and here what they are saying that there are different parts of the world which are either green water limited or blue water limited. So, green water limited means where you have less than 1300 meter cube available per year, and blue water limited is when you have less than 1000 meter cube available per year, per person per year, and about 46% of global population is actually under water stress for both green water and blue water, which means we do not have enough water for the biomass production and also not enough water for actually production of our industrial and domestic use. Then there is about 14% of global population which lives in area where we have enough for the biomass production through the rain fed agriculture kind of thing, but the blue water is very limited, and so they might rely on the imports of blue water. Then there are parts which are green water limited, but they are blue water sufficient, which means that there is not enough interception or not enough precipitation, but they have freshwater lakes that is connected, and you have about 21% of global population, and only 19% of global population by 2050 will be living in areas which are both green water sufficient and blue water sufficient. So, from the sustainability assessment perspective, it is extremely crucial for us to calculate the virtual water content of different products and also identify what is the green water footprint, blue water footprint and grey water footprint of our production processes to be able to strategize managing the water resources all across the world. So, in summary, water footprint helps us in accounting for water consumption in different categories to support production. Green, blue and grey water footprints account for different aspects of water consumption. It follows a life cycle approach for each product to calculate the virtual water content of different products, and it is extremely important for you to remember that virtual water does not mean the water content of the product, but the water that has been required in the life cycle of the production that to support that production. And you can use this approach to understand the risk of water stress for sustaining human activities, along with making decisions on choosing pathways to lower stress. With that, thank you for attending this module on water footprint, and then we will go to the next module where we will talk about nitrogen footprints.